Voltage bootstrapping. In this session, we will briefly examine a very useful dynamic circuit technique for overcoming threshold voltage drops in digital circuits, which is called voltage bootstrapping. We have already seen that output voltage levels may suffer from threshold voltage drops in several circuit structures such as pass transistor gates or enhancement load inverters and logic gates. Dynamic voltage bootstrapping techniques offer a simple yet effective way to overcome voltage drops which occur in most situations. Consider the circuit shown in figure, where the voltage Vx is equal to or smaller than power supply. Vx less than or equal to VDD. Consequently, the enhancement type NMOS transistor M2 will operate in saturation. When the input voltage Vin is low, the output maximum voltage when the input voltage Vin is low, the maximum value that the output voltage can attain is limited by Vout max equal to Vx minus V2 Vout. Figure enhancement type circuit, which is in which the output node is weakly driven. Figure dynamic bootstrapping arrangement to boost Vx during switching. To overcome the threshold voltage drop and to obtain a full logic high level VDD at the output node, the voltage Vx must be increased. Now, consider the circuit shown in figure, where the third transistor M3 has been added to the circuit. The two capacitors Cs and Cboot seen in the circuit diagram represent the capacitances which dynamically couple the voltage Vs to the ground and to the output respectively. We will see this circuit can produce that this circuit can produce a high Vx during switching, so that the threshold voltage drop can be overcome at the output node. Vx greater than or equal to VDD plus V2 T2 Vout. Initially, assume that the input voltage Vin is logic high, so that M1 and M2 have a non-zero drain current and that the output voltage is low. At the same point, M1 is in the linear region and M2 is in the saturation, since ID3 equal to 0. The initial condition for the voltage Vs can be found as Vx equal to VDD minus VT3 Vs. Now assume that the input switches from its logic high level to 0 volts at t equal to 0. As a result, the driver transistor M1 will turn off and the output voltage Vout will start to rise. This change in the output voltage level will now be coupled to Vx through the bootstrap capacitor Cboot. Let I C boot represent the transistor current flowing through the capacitor C boot during the charge up event. Let ICS will let ICS be the current through CS, assuming that two current components are approximately equal. We obtain ICS is similar to IC boot. CS d by Vx CS d Vx by dt is similar to C boot d V out by Vx by dt. Reorganizing equation is the following equation: CS plus C boot d Vx by dt similar to C boot d V out by dt. d Vx by dt similar to C boot C boot Cx by C boot into d V out by dt. It can be seen from equation that increase in the output voltage V out during this switching event will generate a proportional increase in the voltage level Vx. Integrating both sides of equation, we obtain VDD minus VT3 to Vx dVx is equal to C boot by CS plus C boot into integral VOL to VDD dV out. CS equal to VDD minus VT3 plus C boot by CS plus C boot VDD minus VOL. If the capacitor C boot is much larger than CS, C boot much larger than CS, the maximum value of Vx can be approximated as Vx max equal to 2 VDD minus VT3 minus VOL, which proves that the voltage bootstrapping can significantly boost the voltage level Vx. Now remember that in order to overcome the threshold voltage drop in the output, the minimum required voltage level Vx is Vx min equal to VDD plus VT2 by VV out equal to VDD. VDD minus VT3 of Vx plus C boot by CS plus C boot. VDD minus VOL. This equation can be rearranged to give required capacitance ratio as follows: C boot by CS plus C boot equal to VT2 by V out equal to VDD plus VT3 by Vx by VDD minus VOL. C boot by CS equal to VT2 by V out equal to VDD plus VT3 by Vx by VDD minus VOL minus VT2 by V out is equal to VDD minus VT3 by Vx. Note that CS is essentially the sum of the parasitic source to substrate capacitance of M3 and the gate to substrate capacitance of M2 to obtain a sufficiently large bootstrap capacitance C boot in comparison to CS. An extra dummy transistor is typically added to the circuit. As shown in figure, since its drain and source terminals are connected together, the dummy transistor simply acts as a CMOS capacitor between Vx and V out. Although this arrangement contains two additional transistors to achieve voltage bootstrapping, the Resulting circuit performance improvement is usually well worth the extra silicon area used for bootstrapping devices. Here you can see the figure realization of bootstrapping capacitor with a dummy MOS device. Thank you.